So no one joined till now. So I'll start the session after 5 minutes. I'll wait 5 minutes. Maybe some participant will join. Then I'll start. If no one joins, then I'll record and upload the video on YouTube. You can follow, and I'll upload the content also in the Google Drive. So let us wait 5 minutes. Then after I'll start. So today actually we'll solve this some summarized question. So let us wait 5 minutes. So I'll cover the question from all weeks, from 1 to your 12 weeks. So let us start. I think maybe in between students will join. Let us start. So today I'm going to solve the question number, or not the any week number. So extra session today I'm going to take the entire from week your 1 to week 12. I have taken the question well. And I have taken some very interesting questions also here. So the first question is, what is the correct expression? What is the correct expression for the hydrostatic pressure at a point within a fluid at rest? Given the fluid density rho, gravitational acceleration g, and the depth is h. So option A, P is equal to rho gh. Option B, P is equal to rho by g into h, and P is equal to g by rho into h, and P is equal to h by rho. So here you have the four options. The question is the correct expression for the hydrostatic pressure. Remember, hydrostatic pressure, right? At a point within a fluid at rest. Let us assume you have a container and the fluid is in rest. Fluid is in rest means velocity will be zero. Given the fluid density, you have fluid density is zero, and this is the point. and acceleration due to gravity you have considered, and depth is h. So this is h. So at that point, your hydrostatic pressure how much? So remember one thing, please. The value will be rho gh. The hydrostatic pressure rho gh. This will be the correct answer. That is option number A will be correct. And the variation of this pressure will be linear variation. As you can see here, the pH, that is hydrostatic pressure, is directly proportional to your height. Means linear relationship. So it will be like that. Remember this. Rho gh. So your pressure at that point is rho gh. And this pressure will concentrate at a particular point, which is this is a triangle shape, is will concentrate at from the bottom h by 3. So here, please. How you will calculate this p value? So this will be half. You just take the area of rho gh into h. So this will be the rho gh square by 2. This will be your pressure. This is your pressure value, that is Newton per meter square. This is meter. So this is force per unit length. Force per unit width, whatever the width will be the time. Based on the width, if this is your width, the width is unit, so you can say the force is pressure force is here. Pressure force is rho g h square by 2. Pressure force per unit width. Per unit width. Rho g h. So like that. And such type of concept you can utilize in the different that is in your another subject of the civil engineering, which is the soil mechanics, which is very important. So this concept you can utilize. Also, you can utilize this concept in your solving the some gravity type problem. That is a gravitational dam. You know about it. The pressure distribution, like if I draw here, gravitational dam or any dam. If suppose this is such kind of dam is here and water is like that, so pressure distribution, what will be the pressure distribution? Or you can solve like that if it is such type of dam. So what if this is the water depth? So how the pressure distribution will happen? So it is like that. So hopefully you got it, the concept behind your hydrostatic pressure and how you can utilize this concept in another subject and the real life problems. Now let us move with the next question, very important. So what is the condition for fluid static to be applicable in the system? What is the condition for fluid static? Remember please. Option A, the fluid must be incompressible. The fluid must be moving at a constant velocity. The fluid must be inviscid. The fluid must be at rest or moving with constant velocity. So which is the best suitable option? Just think on that. What is the condition for fluid static? So fluid static. means your fluid statics. Very important question, please. Very important. So what will be the correct answer? Whether option B possible or not? I think not, because the fluid is moving with the constant velocity. Yes, it may be correct, but another option we can also see. Here you can see very easily the fluid must be incompressible in visit. Here also it is given the rest. Means velocity is zero. Here velocity is constant. Moving with the constant velocity. Means what is the meaning? The fluid static apply to the situation where the fluid is at rest or moving with a constant velocity without acceleration. So fluid static condition is the acceleration will be the zero. Remember please, acceleration should be the zero. So in both case, when your fluid will be rest, in that case also you can say acceleration will be zero. When fluid will move, you can also say the acceleration will be zero. So here option D will be correct. Remember always. Option D will be correct. Next question. Yes. What is the name of device used to measure fluid pressure in a system? What is the name of device used to measure fluid pressure in a system? Manometer, barometer, hydrometer, thermometer. So just think on that, whether barometer you can use, whether manometer will use, or hydrometer. Or here, one thing is very, very important, measure the fluid pressure or pressure difference, you can say. So which option will be correct? Whether it is manometer, barometer, hydrometer, thermometer. So here the option will be correct, your manometers. As you know already, you have solved a lot of questions like that. This is your pressure, this is your point 5 at point 8, and like that you have this is, let us suppose in the pipe is water, and here you need to put the mercury. So this is your He. So pressure difference with the, so you need to calculate the pressure in this system, how much the pressure at point A. So how we will calculate with the height, head difference and all. So using the your manometer, we can calculate the pressure. Remember this. Next question. What does the Pascal law state in the fluid mechanics? So here this question is about the Pascal law. So option A, the pressure increase with depth in a fluid at rest. The pressure remain constant in a fluid at rest. Option C, the pressure is inversely proportional to velocity in the fluid flow. Option D, the pressure applied to a confined fluid is transmitted transmitted undiminished to every point within the fluid. So just think on that. This is very, very important. And here I'll show you, I'll just discuss one very important question, please. Just think on that. So here, your based on the option, your option D will be correct. This is the Pascal law. When pressure is applied to a confined fluid, is transmitted to every point within the fluid. Remember this. So as per the Pascal law, I'll just show you one example. So let us assume normal, right? So you have such type of container, and this is your water, H2O. But here you have mercury, here you have oil, and everywhere you have your H2O, water. So let us, this is your point, and the level of this is equal everywhere. If the distance from here to here is capital H, this is 1, P1, this is your P2, this is your P3. So here the H1 equal to H2 equal to H3, means the height from top to bottom of container is equal for point 1, point 2, and point 3. And now the pressure at here, the pressure at this location, the pressure at this location, means here I'll say A, B, C, D, E. And the distance for all point is your small h for everywhere. From here to here also small h. So here the question is, so not I'll ask not any questions, so just think on it. I'll just try to explain. So because the level of point A, point B, point C, and point D and point E at the same level, so because your pressure is depend on your what, directly proportional to H, and also density. So for this, the point A, point B, point C, point D, point E, you have everywhere water. So for this, your pressure only depend on what? Because everywhere you have the water means you have the density constant. So your pressure depend directly proportional to small h only. So for each point, h is constant. So that's why PA is equal to PB is equal to PC is equal to PD is equal to PE. Remember this. Now, here at point P, here the density is rho H2O. Here density is rho oil. Here density is rho Hg. Means For this, your pressure is directly proportional to what? Both things, rho and your rho x and your h is constant for. So here you can say P1 does not equal to P2 does not equal to P3. So this will be your understanding, the correct explanation for point 1, point 2, point 3 for the question. So this was from your hydrostatic topic. Okay. So now let us move with the next question. Next question is very, very important. What is the principle of buoyancy in fluid mechanics? The principle of buoyancy. So option E, object submerged in fluid experience an upward force equal to the weight of the fluid displaced. So anyone join? Okay, no one joined till now. Okay, so objects submerged in fluid experience and an upward force equal to the weight of the fluid displaced. Option B, the object submerged in fluid experiences a downward force equal to the weight of the fluid. Option C, the object submerged in a fluid experiences a force proportional to the depth of submersions. And option D, object submerged in fluid experiences a force proportional to the density of the fluid. So here you have the four options. Just think on that. What is the meaning of buoyancy in the fluid mechanics? Okay, so let me just discuss what will be your correct one. So principle of buoyancy. Here option A is correct. Remember this. Meaning, just I'll show you graphically. So let us suppose you have one container. You have one container and this much is water. Let me just put it differently. This much is water is full, completely full. As you will place or object here is this is your container and this is suppose one object is like that. You have one object like that. So as you will put object in this tank, what will happen? So this will be submerged. Let us suppose this is your steel. So this will be submerged in the fluid. Not here, is completely submerged in the bottom level. Here, this will be the completely submerged. So what will happen? So this is your not submerged. This is the case of the sink. Remember, please. The completely this will be the sink. And you have the some. Let us assume you have some wood block. So as you will put this wood in this water, so what will happen? So some wood will be the outside and some part will be the in the inside of the your. So will not take this because the understanding will not be clear. So let us assume the wood one. So as we have put the wood, so this much is in submerged. Let us suppose the height is h. So this much is y. Let us assume is submerged and rest of the part that is h minus y is outside the water. So whatever the submerged part, the volume of this submerged part, that much water will be collected. That much water will be collected in the if you are collecting the bucket, so that much water will be spill out. Whatever the only submerged part, and that will be equal to whatever the here the weight of the fluid, whatever the weight of the fluid is equal to the upward force will be X by the fluid on the object. So that upward force will be equal to this. Or you can say submerged volume of the body will be equal to the water displaced, volume of the water displaced. Or you can also say the weight of the fluid, weight of the this displaced water will be equal to the upward force acting by the fluid on the object. So this was the meaning of your of this line actually. So remember the principle of buoyancy is this. You can also experience at your home with the bucket and some with anything. You can take any material or any object for such kind of or any object means which may be some should be some float that is the some outside. Some parts should be the outside of the water and some parts should be inside the water. Such kind of object you can select, then you can replace. Okay, so let us move with the next one. What is the name of the phenomena where the fluid flow is smoothly in parallel layer with minimal disruption between layers? So whether it is turbulent, laminar flow, transition flow, or the viscous flow. So here, the what is the name of phenomena where the fluid flow smoothly in parallel layers with minimal disruption between the layers? Very important. Still no one joined. Okay. Anyway, I'm recording. So what will be the correct answer? Okay. So this is nothing but very simple things. The laminar flow. Always remember, please. So in the case of laminar, your flow is smoothly, very smooth order like that. In layer wise flow, there is no fluctuation. But in case of turbulent flow, what will happen? In the turbulent flow, this is not like that. Maybe your flow will be like that. In case of turbulent flows, just remember, this is your laminar, which is smooth parallel layer, and this is your turbulent. Remember. Next, moving on the next question. So, what is the Reynolds number used for the fluid mechanics? What is the Reynolds number used for the fluid mechanics? To measure the pressure gradient in the fluid, to determine the velocity profile in the fluid, to predict whether flow is laminar or turbulent, to calculate the hydraulic radius of open channel. So, very important question. So, what will be the correct answer? I have some numerical questions also, but why I'm just going through very simple question because maybe some new student who not have background of the fluid the fluid mechanics till now. So for those student, I am covering some simple questions also. I have some numerical from the previous gate questions, so I'll cover these things also. So, but I'm going very slowly with simple questions. Just think, what is the Reynolds number in the fluid mechanics? So here, fluid mechanics means not only your pipe flow, also we are considering your open channel flow, that is river flow and all, and also the gas flow also it come in the fluid mechanics. Remember, liquid and gas flow. Okay. So Reynolds number is nothing but your R is equal to inertia force by viscous force. That is rho average velocity into d by dynamic viscosity. Here d is your 4 AC by P. 4 AC by P or DH I'll write here. So for pipe flow, your DH will be So this is pi. Okay. So the diameter of pipe is D. Small d I'll take here, or capital D I can also take. So here for AC, area of cross section, pi by 4 into D square. P is perimeter. P is perimeter means pi D. 4 will be cancelled out, pi will be cancelled out, D will be. Only DH is equal to D for your circular type of pipe. So that's why you write Reynolds number for circular pipe rho VD, that is diameter of the pipe, into this is your Reynolds number. So this non-dimensional number used for your describe whether the flow or predict whether the flow is laminar or turbulent. So this is the key importance of Reynolds number, and when it is 2000 or equal to Ra is equal to or less than 2000, then laminar. If Ra is for pipe flow, I'm writing, please. If Ra is greater than equal to greater than not equal to 4000, this is your turbulent flow, or in between your transition flow. When Ra is greater than 2000 and Ra is less than 4000. So this is the case of for pipe flow. Similar. So here option C will be correct. But also I want to discuss for the open channel. For open channel, your RE when less than equal to 500, then open channel. Then it is laminar. When RE is your greater than 1000, it is your turbulent. When RA in between, that is less than 500, not less than, greater than 500, and R is less than 500, 1000, then this is the case of transition. Remember this. This is turbulent, this is laminar, this is transition. So this is the whole idea of your Reynolds number. Always remember, very simple. Okay. So next question, which of the following is correct expression for the velocity profile in laminar flow through a circular pipe, whether parabolic, linear, exponential, irregular? Very important question. So anybody join? Let me just check. Oh, no one join. Anyway, recording is going on very well. So flow, which of the following is correct expression for the velocity profile in laminar flow through a circular pipe? Very important. So let me just discuss. You have one circular pipe. This is your circular pipe. So for laminar flow, your velocity profile will be the parabolic. After fully development length, remember please, this will be the parabolic profile. I'm not able to draw correctly, but okay, anyway, yes, think this is parabolic. Parabolic after the fully development length, or this is development length, not after. What is development length? Once your fluid will enter in the pipe, what will happen? This uniform velocity, assume if the fluid is entering in the pipe with uniform velocity. So due to this wall effect, your velocity diagram will be like that. So due to this wall, the boundary layer formation will happen from this side also. After that, it will be the dimness and velocity profile will be like that. Up to that, it will be the parabolic. Up to that, it will be the parabolic, then uniform. Similarly, here, up to that is parabolic, parabolic, then straight. Similarly, up to here, parabolic, up to here is parabolic. Up to here is the your parabolic, then straight. But after that, the fully your this parabolic. After that, then there will not any change in the velocity diagram. If you will draw here, the similar velocity diagram you will get, not any change. Okay, this was about laminar flow, remember. But in the turbulent flow, what will happen? In case of turbulent flow, your velocity diagram will not like that. In case of turbulent flow, when your RE is greater than 4000, in turbulent flow, here will be the little bit straight. At the boundary level, it will be the straight, then logarithmic. So this is your logarithmic. This is your linear, not straight, linear profile. So remember this. In case of turbulent flow, you have the two combination of graph. One is logarithmic type and another is your linear. But in case of your laminar flow, only parabolic. Very, very important. Now let us move with the next one. What is the correct equation for Bernoulli's principle in fluid mechanics, neglecting the viscous effect and external forces? What will be the correct equation for Bernoulli's principle in fluid mechanics? neglecting viscous effect and external forces. So what will be the correct equation? We know already P by rho z. This is a very famous question, famous equation. V square by 2z plus z is equal to constant. So if you want to write in terms of like that P, so multiply everywhere rho g. P by rho g into rho g. V square by 2g into rho g plus z into rho z is equal to constant rho z. Again, it will be the constant, and here rho z will cancel out. Only P will remain plus g will cancel out. So V square by rho V square by 2, and here rho g z. Just compare which option is correct. P half rho V square. Okay. In the question is taking h, so I'll take h also here. So that will be easy for understanding. If this is h, so we will get h. So P plus half V square rho V square plus rho g h equal to constant. So this will be the correct option number 8. Remember this. Next one. What is the equation of motion for inviscid fluid? Remember, equation of motion for inviscid fluid expressing the conservation of momentum. What is the equation of motion for inviscid fluid expressing the conservation of momentum? As here, the Navier-Stokes equation, Euler equation, Bernoulli's equation, and the continuity equation, all is given. Very important. One thing also remember here is the conservation of momentum is written. Now we are moving with uh, some different type of question, not very easy. What we are solving above. Yes, so here you know already the Navier-Stokes equation is the your motion of viscous fluid. But in the question is asking inviscid. Means if your mu will be the zero if inviscid. So if you will, this term will be zero from Navier-Stokes equation. If it is inviscid, so you can go with this. That is your Euler equation will be the correct. So remember please your Navier-Stokes equation is the what? motion of viscous fluid, not inviscid fluid. So change in velocity with respect to time plus this is written in the vector calculus. So, and in the previous session, I have told how it is important, how we can write this from your coordinate to a in this form mu del v square plus g. Remember. Okay, so this is your Navier-Stokes equation. Equation of motion of viscous fluid. And this is option A is equation of motion for inviscid. Remember, please. Okay, next question. What is the correct form of Navier-Stokes equation? What is the correct form of the Navier-Stokes equation for an incompressible fluid? What is the correct form of the Navier-Stokes equation for an incompressible fluid? Remember, incompressible fluid means rho is constant. So whether option A, B, C, and D, incompressible fluid. We are not written like that, inviscid and all. So remember, please. Okay. So the correct form of the Navier-Stokes equation is this one for incompressible fluid. Remember, please. Option A. Now, what is the correct form of the continuity equation for incompressible flow? Again, what is the continuity equation here is continuity. Only condition here is incompressible, not steady incompressible. Remember, please. Not steady, only incompressible. So whether option A, del rho by del T plus del operator, rho V. Option B, you can read. And option C, your never is to take, and option C. So which option will be correct? So yes, if here is the condition only incompressible flow, so your option A will be correct. But the same question if framed like that, your flow is the steady and incompressible both. And what will happen? You will come up with, because steady means your change in time with respect to time will be zero. So let me just write very clearly, del rho by del T plus del operator equal to 0. As this is two condition, so what will happen? This will be the zero. So you can remain with, and rho is constant, so you can write like that also. So this is your condition for continuity equation. This is continuity equation condition for steady incompressible. So like that. And how can you express like that? Your del operator is nothing but del x del y del yz plus del y del zk. So this is the del operator meaning, and your v is nothing but uy plus vz plus wk. When you will multiply these two things, you will get what? Del by del x I plus del by del yz plus del by del k del z k cap into uy plus vz wk. After multiplication, I del u by del x del v by del y del w by del z. You will get this expression after multiplying. So you can write very clearly here del u by del x plus del v by del y del z equal to 0. So this equation you can write like that also. Okay, now coming in the new one. What is the correct expression for the dynamic viscosity mu in Navier-Stokes equation? What is the correct expression for the dynamic viscosity in Navier-Stokes equation? Whether mu is equal to rho v L by Re. L here is the characteristics length, please. Mu is the rho L square is equal to 2. Option B. Option C, rho v L square by Re. And option D, rho v square L by Re. So you can think very easily. So here option C will be correct. Remember this. Option C will be correct. Okay. So next question. What is the correct form of Bernoulli's equation for an ideal incompressible fluid? Ideal incompressible. Correct form. Whether v square by 2 gz plus rho by p by rho. Option B, v square by 2 gz plus p equal to constant, p plus rho gz plus rho v square constant, p plus rho gz constant. Here you have the two condition. Your fluid is ideal and incompressible. two conditions you have in your hand. So you know one thing, this expression you know very well, P by rho z plus B square by 2z plus Z is equal to constant. So everywhere you can see very clearly your P is free. P, here also P, and here P by rho. So let us move with the first one. So let us make this P by rho. So for making the P by rho, you have to multiply everywhere is Z. P by rho, join. So after this question, I will take 5 minute break. Okay. So P by rho into G plus V square by 2Z into G plus Z into G is equal to constant into Z. So again, you will get the constant, but here P by here is rho Z. P by rho plus Z will be cancelled out. So V square by 2 plus Z is equal to constant. So the first expression is coming very well. So remember this equation is your for ideal incompressible. Okay. So let us okay. Here is the incompressible means you know already the rho is constant. So if the rho is constant, okay, yes, you go with the option number A. Yes, option A will be correct here. One. Okay, the next question. What is the correct expression for the Reynolds number Re in the fluid mechanics involving characteristics length, velocity, and the dynamic viscosity? Re. So rho V L by mu. So this is the simple one. Rho V L by mu. Option A will be correct. Next one. What is the correct expression for the Darcy's-Weisbach equation describing pressure loss in the laminar flow through pipe? So this is the your question. So I'll take a 5 minute break so you can solve the question, or you can also take break. So now let us solve the question. So the question number your, let me just, okay, everything is fine. What is the correct expression for the Darcy's-Weisbach equation describing the pressure loss in laminar flow through pipe? So what will be the correct expression? So this is a very uh, important one. You can expect the and question from here in your final NPTEL exam. So here option B will be the correct. Your delta P is equal to FL by D rho V square by 2. Means your delta P by rho is equal to FLV square by P by rho Z here, 2ZD. So you can write, then this is your in terms of loss, head loss, HL is equal to FLV square by 2ZD. Remember this. Now the next question is, what is the correct expression for the Hazen-Pauli equation describe laminar flow through pipe? Hazen-Pauli. This is also very, very important. Direct question you can expect. So again, here your option A will be the correct. For this question, option A. Q is equal to 5 due to the power 4, 128 mu del P by L. So this will be your correct answer. Next one. What is the correct expression for drag force FD acting on a sphere in a fluid flow, giving given the fluid density rho, sphere radius r, velocity v, and the drag coefficient c? So what will be the correct? So you know already the drag force is nothing but drag force half rho a v square by CD here. CD half rho a v square. So here is your, what will be the A? Here is L, one another length term will be here. Rho V L V square. So you can write your drag force. You can compare from here. So once you will compare, you will get the your not like that. Sorry, not L. Once we will, this is the expression, final expression, half rho A V square. Once you will compare this, you will get what? This one, half rho, this is pi r square area and V square C. So option A will be correct. Remember this. Next one. What is the correct expression for the pressure distribution PZ in of fluid at rest in terms of density, gravitational acceleration, and depth. P naught here is atmospheric, you can say the atmospheric pressure, or pressure at the surface, you can also say. So what will be the PZ? PZ is nothing but P naught plus rho GH. If it is at the depth of Z, so at the place of H, I can, or you can also think J. So just compare. So I think option A will be correct. So this will be the correct answer. Initially, we have solved this question already. Next one. Another questions also have before moving on the next question. Okay, let us discuss this question, then I'll move on to the next question. So for the Bernoulli's equation, very important question. Question number 30. For the Bernoulli's equation to be applicable in a fluid flow situation, which of the following condition is are to be satisfied? Maybe here option one option correct or more than one option correct, as here you can see very clearly written. So Bernoulli's equation, as you know, as I have discussed very much here, P by rho z plus many times I have discussed V square by 2z, Z is equal to constant. So for deriving this, we have assumed already flow is steady, flow should be steady, incompressible, and frictionless. So these are the main three. So you can compare from the list. These all three option is correct. But flow may be rotational or flow may be irrotational. In case of rotational flow, your Bernoulli's equation you can apply at a particular streamline. But if your flow is irrotational, if the rotational flow, in the rotational flow also you can apply the Bernoulli's equation, but the condition is you can apply only a single streamline, only corresponding a single streamline, the same streamline. But in case of your irrotational flow, you can apply Bernoulli's equation anywhere, anywhere the domain. You can apply here and here also, irrotation. But in case of your lamin this rotational flow, you cannot apply. You can apply only the this streamline. So here is written very well. The flow along a streamline. General case, when we apply the Bernoulli's equation along a single streamline, the flow can be rotational or irrotational. When you are applying a single streamline, it may be the rotational or maybe the irrotational. That means even if the fluid has vorticity, that is rotation, the Bernoulli's equation is still valid along each individual streamline, but the constant will differ from one streamline to another streamline. Okay, so P by rho z V square by 2, P by rho V square by 2, and Gz constant along a streamline for rotational flow. Flow through a entire flow field. This is special case. If the flow is irrotational, that is vorticity is zero. If the vorticity is zero in your fluid, then Bernoulli's equation applies anywhere in the fluid flow, anywhere in the flow field, not just along the streamline. So this is very, very important. And in that case, constant value P by rho plus V square by 2 and Gz is the same for all streamline. Remember. So this is constant everywhere. Example, you can see example also. The around an airfoil, the flow of air is approximately irrotational outside the boundary layer. So Bernoulli's equation apply anywhere. In that reason, inside the boundary layer or the near the wall, the flow rotational due to viscous effect. So remember here, the rotationality in the fluid is come due to the viscous effect. If the viscous effect is negligible, you can say the fluid is irrotational or rotationality negligible. Bernoulli's equation apply only along the individual streamline, not across them. Remember this. So here is some derivation. Here you can the derivation of the streamline, your Bernoulli's equation, how it is derived with using the Newton's second law. You can go one by one, and you can go with the very simple way it is written here, in the very simple way. So, and after the final expression, as you can see here, this is your flow energy, then kinetic energy, then your potential energy. The combination of all three is constant here. Okay, so here the final definition, the sum of kinetic potential and the flow energy of fluid particle is constant along a streamline during steady flow when compressibility and the frictional effect are negligible. So these three main, that is the main three assumption is your behind this equation is your steady flow, incompressible, and another one is your this frictionless or yes, or invisible. Okay. So from here, the detailing of given here, as you can see in the derivation, at this phase, the PdA is written, and at this phase, P plus dA is written. So as you know, the water will flow or the fluid will flow, fluid is flowing in this direction, means from high pressure to low pressure, from high pressure to low pressure. So PdA will be more, your PdA will be the more than this. Then only your the fluid flow is possible. Remember this. Here is the case. If your PdA, the pressure at this point, this one will be the more than this pressure, P plus dA. So if it is more, then why we are adding something here, P plus dA? Why we are adding? So uh, for this reason, I have put it lot of here the information regarding why the why pressure decrease when the fluid accelerate. Fluid accelerate means fluids move from here to here with the velocity increasing decreasing. So like that, you can read one by one. And what is the meaning of dP? That why P plus dP. So what is the meaning of dP here is given. And another thing, very, very important, here is given one thing, why we are considering P plus dP. Because initially the upstream P is more than here. If you will see, we are adding something. We are adding. If we add something in the P, then what will happen? It should be the more. But this is more. This is the, you can see this is the contradictory. So, but why we are adding in the differential, in the calculus, here it is very important. One thing is written. Take a thin fluid element with the length dx, cross-sectional area A. So pressure at upstream phase E and the pressure at downstream phase is P plus dP. Just think on mind. Just keep in mind. Here dP is just differential change in the pressure over the dx. It can be positive or negative. Force on the fluid element. The force on the fluid element upstream P plus A and force is downstream is this. So what will be the net force? Net force means just your take the difference between these two forces. So upstream, downstream. Once you will take, you are what you are come up with minus AdP means your pressure net force means your pressure is decreasing. Net force is coming minus AdP means your pressure is decreasing as you are moving in the upstream to downstream. Meaning of this. So without considering, so meaning here is you have to not consider initially minus here. In the differentiation, in the differential calculus, this is because we are solving with the directions. We are taking we are taking plus in this direction, we are taking minus in this direction. So this will be your P plus dA will be, as you can see here, it is coming minus A. It is showing. What is showing? So the net force upstream force is, so the net force is upstream force minus downstream force. We are getting this one. And what is the pressure decrease? So if the pressure decrease downstream, so if the pressure is decrease in downstream means when the flow is possible when pressure high pressure to low pressure means the pressure is decreasing in the downstream direction. So this is written here. So as you can see, this is a minus F net is minus A, and this is your pressure. Pressure is decreasing, so that's why if you will put here at the place of your dP the minus dP, you will get the positive value. Means here dP is just magnitude of the pressure drop and the net force is positive, which means it point in the directional flow. Net force is positive means your net force here is coming negative, but because your pressure is decreasing after putting the minus dP, then you will get this net force. Means net force is positive means your flow, your force is directed because here you have considered positive is in this direction, upstream. So your force is positive means your fluid, this make the perfect physical sense. Physically, when the pressure drop downstream, the fluid is pushed forward by the higher upstream pressure because your force is directed this side. So flow is from this side to downstream side. So this is the overall. Once you will go one by one, the step by step, you can get definitely very interesting things. Remember, please. So now let us move with the next one, next question. Next question is also very, very important. These are the gate previous year question. A horizontal pump, a horizontal jump is formed at 5-meter wide rectangular channel. This is your 5-meter wide rectangular channel, which has a horizontal bed, that is theta is equal to 0. Theta of bed is equal to 0. Carrying discharge 15 meter cube per second. The depth of water upstream to the jump is, that is your before the jump. I'll take the y1. Before the jump is value is 0.5 meter. Power dissipated by the jump. Power dissipated by the jump. in kilowatt. So this is the question. So meaning, I'll show you the visually. Let us assume spillway and water is, here is Y1 or sometimes H1 you can say. You can say H1, Y1, whatever. And this is your Y2 or H2 you can say. And here is jump is formed, hydraulic jump. So in the formation of hydraulic jump, you lose the energy. Means if this is 1 point, if this is 2 point, this is E1 and E2. So loss of energy, how much? Loss of energy is how much? E1 minus E2. So this will be your loss. So how you will calculate the power dissipation? So once you will get the loss, then you know the water, the power formula for the water case, rho Q Z H. This is the power formula in case of the water power. So here rho Q G and H is the, that is the power due to the H height or H head, but here you have lose the head, whatever you will get the energy. So you are losing something here. So E1 minus E2, this will also give you in meter. So unit will come in the meter. So now this will be your final answer after the calculation. Your power loss, your power loss will be rho Qg E1 minus E2. So what is E1? E1 is nothing but Y1 plus V square by 2Z. What is E2? Nothing but Y2, here is the V1. Y2 plus V2 is square by 2Z. How you will calculate V2 and Y2? Discharge is equal to nothing but area into velocity. So area is, so velocity is your discharge by area. So V1 will come, discharge is your, discharge value is how much? 15. 15 area is B into Y. If it is 1, then 1. So 15 divided by B is already given 5 into the value is 1. Y1 is 5. So 30 by 5 means V1 is 6 meter per second. Similarly, V2 is 15 divided by B 5 into Y2. But you don't know Y2. How you will calculate Y2? So you know one formula. Y2 by Y1 for rectangular channel. This is, remember, for half minus 1 plus root under 1 plus 8 FR1 square. And what is FR1? FR1 is nothing but V by GY1. So this is your 6 divided by 9.81 into Y1 is nothing but your 0.5. So this will come around Let me just calculate. So 6 divided by 9.81 into 0.5, take square root, 2 point, this is your coming 2.214, and 6 divided by 2.214, it will come 2.7. 2.7, your fruit number is 2.7. So here you can calculate very easily. This is y2. So y2 is y1 by 2. Y1 is 0.5. This is your 2 minus 1 plus root under 1 plus 8 into 2.7 square. Remember, I have very limited space. So once you will calculate this, so 8 into 2.7 square, it is coming 58.32 plus 1 and take square root, it is coming 7.7 minus 1, 6.7 into 0.25, it is coming 1.675. So your y2 value is coming 15 divided by 5 into 1.675. So 5 into 1.675, 8.375. 15 divided by 8.375, it is coming 1.8 meter per second. Now you can put here y2 is 1.67, y2 is 673 or 5, I don't know. Okay, 673 I think is it, plus v square by 1.8 square by 2z, 2 into 9.81. Okay, so just think on that what I am doing, just think on that, keep in mind 1.8 square divided by 2 into 9.81 plus 1.67. So 1.83. It is coming, E2 is 1.83. E2 is coming 1.83. E1 is coming how much? Where is the E1? Yes, E1 will be your 0.5 plus 6 square divided by 2.2 into 9.81. E1 will come around, let me just calculate, 36 divided by 2 into 9.81. So 1.83 it is coming. 1.83 plus 0.5. 2.33. So it is coming 2.33. So now you can put here 1000 into 15 into 9.81. And when we will minus this, 2.33 minus 1.83. So 2.33 minus 1.83, it is 0.5. 0.5 into 9.81 into 15 into 1000. So this will come 74.290 watt. So you have to divide with the 1000. You will come up with 74.29. 74.29 kilowatt. So this will be your final answer, 74 point. Here you can fill 74. Round off of the integers, so 74 you can write very clearly. So I have the solution also, how I will proceed. So these are the expressions. So 72 it is coming around. So I think somewhere the point value here and there. So no problem. 72 is coming, or as per the solution, it is coming around 74. It's okay. Okay, now the next question is, this is also very, very important question. A 5-meter wide rectangular channel. Here also you have the wide rectangular channel of the 5 meter. Okay, carries discharge 10 meter cube per second. Depth of the flow is 1.5 meter. Uniform flow, remember please. To produce critical flow condition. Here you need to produce critical flow condition. Critical flow condition without affecting the upstream condition. Without affecting the upstream condition. Without affecting the upstream condition, the channel bottom elevation should be raised in meter. Round off up to two decimal place. Take the kinetic energy correction factor is 1 and acceleration gravity is 9.81. So how much your bottom will increase without affecting the upstream condition? So this is your flow direction. How much this jet should be increased? So this is the question. You have 5-meter rectangular channel. The condition is to produce the critical flow conditions. Remember. So here I have the solution, step by step solution. So how you will proceed? Just I'll go through because we don't have that much time. So I'll not calculate here. Calculation is already ready. Okay. So the width of the channel is 5 meter. Discharge is given 10 meter cube per second. Depth is 1.5 meter. Acceleration due to gravity is 9.81, and your kinetic energy correction factor is alpha is 1. There is no energy loss. So compute a specific energy at upstream. So what will be the specific energy? This formula. So you have each everything here 1.5, and your velocity is equal to discharge by area. So you have already the discharge and area. So you come up with final velocity 1.3. So your specific energy at upstream will be 1.59. 1.59 meter. Now compute the critical depth YC. For rectangular channel, the critical depth is YC is equal to Q square by Actually, the formula generally we would remember this one, Q is squared divided by G power 1 by 3. But when you will write in terms of your total discharge, this is small q is nothing but capital Q by B, or small b if I am using. So when you will put this at the place of Q, when you will put in this equation, you will get this one. So after calculation, your critical depth is coming like that. So compute the specific energy, critical specific energy. Your critical specific energy is this. So now compute required rise in channel bottom. So we want to reduce the specific energy from upstream value from this to your critical. So range of the channel bottom is E minus EC. Your final answer will be 0.48. So here idea is in the question. What is idea? How you will think. This is very, very important. The calculation is very easy. Calculation is very easy, but how you will think, how you will approach this question, this is very, very important. So I'll explain, and after that I'll close the session. Today's session I'll close. Okay. So without affecting the upstream, and you need to produce the critical flow conditions. So let us assume at the section 1, here you have some energy, here you have some, here you have to create what? You have to create your energy minimum. That is critical energy, E critical. You have to create in the question is given. Because if you will not create anything here, so energy at that place and energy at that place will be the same. If you are going to increase the hum here, then what will happen? Your energy should be disturbed, but energy should, if you will not take consider how much the height of this hump should be increased, then what will happen? Upstream flow will be affected. Remember, so you have to create this hump. The upstream flow should not be affected. So only the possible way already in the question is given. If in the question is the condition was not given, so you also consider this is possible only when you will create here something you achieve at that place. Use specific energies at critical level. So already the question is given. This is the advantage of question. So here you will calculate the energy. Here also you will calculate the energy, minimum energy. That is your critical energy. And whatever will be the difference at that place, that difference will show you the raise in the Z rise at that place. Because when anyhow at any condition, energy at that place and that place will be the same. But as we are increasing this Z value, so this will also consider, because once we will write EC plus Z is equal to your E1, this Z rise E1. So energy at both places. So like that, just think on that. So this this is the way of approaching such type of question. So, okay, I have lot of question, but we don't have the time. Okay, I'll upload this. All questions have the solutions. This is the advantage. All questions have solutions. This is a very, very advanced question, very simple questions also given. Uh, the how the flow is changed when you assume the linear profile and the parabolic profile, how we will solve the parabolic profile and all. This question is very, very important. You can go with this. Very important question. Solution is already given. Don't worry. Similarly, these are the very simple question. These are the very simple question and the simple answer is also given. These are the very simple. Here the manometer question is given. Your hydrostatic question is given. So you can go one by one. Here, whatever I was discussing previously, how the linear profile will vary, also it is given. So solution is given. Don't worry. So if anyone have any doubt, you can mail me also. I'll write here my mail ID, opmoria, IIT14 at gmail.com. Another mail ID, om1996 at the rate iitg.ac.in. So I have these two mail ID. If anyone have any doubt, you please send with a screenshot in which question you have doubt, then I'll reply back with the video or the with solution also. So okay, thank you for today. So let me just close the session. So thank you all.